All right, we're going to talk rates of change, which will lead into derivatives in Chapter 3. This is the last section of Chapter 2, so let's get on this. Um, with this straight line, I want to talk about the concept of slope because derivatives all are based around slopes. And so let's say we have 2 points, one here and maybe one out here, and we call this x1 and this x2, just points on the x-axis. Okay, and they have corresponding y values, which we'll do here in green. Say this point is here, and just kind of eyeballing it, maybe right here, and then over here somewhere, and here somewhere, their respective y values. So we'll call this y1 and y2, just values on the y-axis. You can pick any points for this you want. And this is basically an Algebra 1 or Algebra 2 concept. But the concept of slope, which we know as m, is the change in the y values divided by the change in the x values. So if we were to take this distance right here, that would be delta y. That would be the change. Delta means change in. So the change in y values, or the difference between the two. And this distance here would be delta x. So if we divide these two red distances, I'll actually trace that and make that red. But if we divide these two, the y by the x, we get the slope of this blue line right here, which tells us actually a whole lot of things when we start talking about curves, which is what calc is all about. But we know from Algebra 1 and training in the past that the difference between the y2 and y1 is simply y2 minus y1. And for the x, delta x, it is x2 minus x1, which we know as the slope formula. I'm sure that's bringing back good memories. But that's basically the slope formula. All right, but what if we talk about a curve? Okay, so let me try to draw a very dramatic looking parabola. There we go, not too bad. Let's say this was some falling object's speed or something like that. We know that objects that fall, free fall, make a graph very similar to that right there, actually, because they speed up over time or accelerate. Well, what this is going to lead into is you being able to figure out the speed of that object any point on this graph, which is something that my physics students aren't going to get into, is the calculus of physics, but you guys will get this. All right, now let's do the same sort of concept here with two random points. So we'll have a point, say right here, being x1. This is our x-axis and our y-axis. And a point maybe here called x2. Okay? And let's color code this similar. Maybe about right there. And these will come over to our y values, which we'll call this y1 and y2. So the coordinates of these points would be simply x1, y1, and this would be x2, y2. All right. And if I drew a straight line through this, I need a really, really good color like bright purple or something like that. If I drew a line that went right through those 2 points, that's good. That purple line is known as what's called a secant line. S-E-C-A-N-T line. And a secant line passes through a curve in 2 points. So it's going to hit it here and here. Now, if I were to find the slope of that purple line, that would be what's called a rate of change between these two x values. Okay, that would be called a rate of change between the x value and the y value. It would be the speed, or whatever, if we're talking speed here, of the difference between these 2 points. Okay? So looking back at the concept we just did, this, and I'll use red again, this value here would be delta x. That value here would be delta y. And we know that delta y divided by delta x would equal x y2 minus y1 over x2 minus x1. And that's the slope again. But if we call these 2 points, these green points here, let me make them green again. There we go. If we call these 2 points here maybe point P, and point Q, that's usually how it's done. As we shorten this distance, now you're going to have to use your imagination on this a little bit, but if we could imagine what if this purple line here was rooted to these 2 green points, and I could take this right here and pull this green point down to here. Okay? If I could pull it down to say right there, well then this purple line would look something like that, which dramatically affects its slope. Okay? The slope is completely different than the other one. And as we shorten the distance between, now remember, when I pull this green point down here, that's also pulling this value, this value of x2 that way. Okay, it's pulling it over here. But as I shorten it down, closer, we don't get a secant line anymore. When they go down and they touch each other, we have what's called a tangent line. So if we could imagine a curve going up through here, and these 2 points becoming infinitely close and finally being right on top of each other, where the distance between these 2 points are 0, then we would have what's called a tangent line, and that would be something like that. It would hit the point once. That's called a tangent line. Okay, tangent line hits 1 time. Secant line hits 2 times. Wow. Let's just do that over. 2 times. Intersects 2 times. A tangent line hits it once. So a secant line's all fine when you want like an average speed between 2 points, but if you want to know the instantaneous rate of change or the instantaneous speed at that point, you need what's called a tangent line, which involves you shrinking this distance or pulling x2 closer and closer to x1 to where they're literally on top of each other. And that is called taking a limit. And when you do that, you, my friends, it's what's called taking a derivative of this. So this is what's called when x2 gets infinitely close to x1, that's called taking a derivative or finding an instantaneous rate of change. So let's go back and review. When you have x1 here, the yellow, x1 and x2 here, and this would make this purple line, we'll call it number 1 here. That purple line number 1, that is a secant line, and that's called a rate of change between x1 and x2. Now there's lots of problems we'll do first with secant lines, and then we'll take limits of it, and then we'll start doing tangent lines. And I think that's a good place to stop for this one. See ya.